Okay, let's get started. So we want to cover a lot of material today, so it's going to be pretty fast, I hope. Firstly, how was the quiz? Okay, yeah. So only one question was something that we hadn't seen earlier, right? And so we'll just do that. Everything else we had done pretty much in class, and you just had to, repeat what you had done in class, right? Okay, so we'll quickly solve that one question. Do you recall that? So I had said that right? This was a signal that was defined, and I asked you to find the DTFT of this signal and plot it, right? So what is the answer to this? Right? Is that true? Am I missing something? Right. So this comes with an additional constraint. And why is that constraint? Okay. One of you, maybe in the back. Why do we need to have that constraint? Yeah, raise your hand and you can answer. Yeah, go ahead. Oops. Yeah, quickly. So why do we need mod A to be less than 1? Okay, anybody? Sorry? What needs to be less than?
It is infinite if so commonly it should be less than.
Okay. So essentially it goes back to the definition of the stability, right, of a signal, right? So if that has to be, so what was the condition we had? should be what? Should be right. And this is satisfied for this when mod A is less than 1, right? Okay, so that's pretty clear. And so how do you want to plot, how would the plot look like? So if I want, so this is the general shape of how it's going to look like, and it's periodic. And this is, and what's the phase of this signal? This how much? That follows from this, right? You know how to do that, right? You can make this, so the complex number, you make this real in the denominator by multiplying by the complex conjugate of this, the numerator and denominator. Then take the imaginary part, that's going to be minus a sine omega. The real part is 1 minus a cos omega. Okay? And the phase is going to be tan inverse of that. Okay? And so that is typically going to look like okay. So this is all I wanted. And one thing I want you to remember is, even with the Fourier transform and the Z transform, we want, when we specify this, we are actually specifying both this and this, right? So when I ask you to plot something, I am expecting both of these things, because that is the complete representation of this complex quantity that you have here. Okay? Just so it's clear to all of you, when I say plot, it simply doesn't mean the magnitude spectrum. I mean both magnitude and phase. Okay? And the reason is obvious, because this is a complex quantity, and to define it completely, you need to have both the magnitude and the phase represented, right? Any questions about this? Fairly straightforward? Okay, that's good. So let's continue. So before we go ahead, so I'm sorry, I don't know you. I don't recall your name. You had a question about what we were doing last time when we left off. I think we had a summation of the Dirac delta functions, and I think you had a question about I forget. You don't recall? Okay. If you do, let me know. Okay. So where were we last time? So we defined a couple of exceptions, or try to make the DTFT more general, right? So we included the case when we want to have square summable sequences, right? And we also wanted to include the case where a sequence is neither square summable nor absolutely summable, right? And we discussed a couple of examples in that context. Do you recall those? So for the square summable, what example did we give? We gave the example of the low pass filter, right? And when we said that when we take the inverse Fourier transform, what do we get? We get the sinc function, and that sinc function is not absolutely summable, right? But it is square summable, correct? And we saw that. Did any of you try to go and do the proof of that? Did anyone try that? If you haven't, go ahead and try it, because that is how we showed that the sinc function is not actually absolutely summable, right? There are many ways of proving this, and you can try to do that in one of several ways. One example that we gave was this will actually become the log. There's one more example where you can show that S of n to n is actually going to be greater than S of n plus some constant term here. And so you can have a recursive proof of this as well. Okay, but this is just an aside. The main point is that the sinc function is not absolutely summable, and so we had to make a relaxation of the definition of the DTFT. And what relaxation did we make? We defined what? We defined this, right? Right? We defined the Fourier transform on this window, and we said that for square summable signals, although this is not going to be finite, the claim, we are not going to prove this, but the claim is that for such signals where this is infinite, the claim is that, but if it is this, it is square summable, then this error that we have, that is actually going to go to 0 in the limit So this is essentially the energy in the error, right? If you recall from the Parseville's theorem, we said that in the Fourier domain, this is how we are going to define the energy. And this is actually the energy density, because we are multiplying with this with frequency, right? So this term here is what is known as the energy density. And in the limiting case, this is actually going to go to 0, okay? We will not try to attempt to prove this here, but this is a result that we are going to say is what is going to help us when we work with signals that are square summable, okay? And in the example that we looked at, we were going to have the sinc squared, right? So sine omega Cn by pi n, the whole squared, okay? And then you have, instead of 1 over n in that case, you're going to have and that is going to be definitely bounded, okay? So this is one of the claims we made last time, or one of the extensions we made to the regular definition of the DTFT, okay? So one question, just so we are all, trying to be on the same page here. So why did we define the DTFT in the first place? Why do we want to define the DTFT of a signal? So do you recall the definition of the DTFT of a signal?
To analyze the response of a system to different frequencies.
Right. So we want to use this as an analysis tool, right? And why did we choose the complex exponential? Right. It is an eigenfunction. So essentially, when you hit a system with such a signal, the response of that is going to be completely because of how the system is defined, right? So you have essentially your y of n is h e to the j omega, or y of e to the j omega is h of e to the j omega times the input signal, right? And in our case, if x of n is e to the j omega n, we find that the complete system response can be found by using such an input for your system, right? Is that clear to everyone? Okay, because we are soon going to accelerate today, and I just don't want someone to be left behind at this point. Okay, is that clear to everyone? Why we defined the DTFT? And so why did we call one equation the synthesis equation and one equation the analysis equation? right? So what do you mean by analyzing a signal? Okay, so you essentially want to look at how many frequencies or how differently the frequencies are present in a given signal, right? Or it could be a system as well, correct? So in case it's a system, what happens? When I look at h e to the j omega, what information is it giving me about the system? Say, for an example, we've been looking at two typical systems in the class, right? One is the accumulator system and one is the backward difference system, right? And we also saw how h e to the j omega for these systems look like in the last class, right? Say, for example, the backward difference system. What did h e to the j omega give us? Like when you looked at the magnitude spectrum, what did it tell you? Right? It's a high pass filter, but how did you arrive at that conclusion? Right? Right? So what did the frequency response tell you? Right. So essentially when you look at the frequency response, so what did we have when we looked at h of e to the j omega for, what was it? 1 minus e to the j omega, right? Is that what it was for the differencing operator? Right? That's straightforward, right? You have delta n minus delta of n minus 1, correct? Correct? And how did the magnitude spectrum look like? So what happens when omega is 0? So you have 0, right? And what happens when omega is, say, pi or minus pi? So you are going to go something like that, right? And this is going to be 2. Right? Was that how it looked like when we looked at the frequency response of the low pass, of the high pass system? We have done this, right? I hope you're not seeing this for the first time. Okay? So my question again to you is, just to be sure we all understand why we want to use DTFT. So by looking at this system, what is it going to tell us? We also discussed in class that frequencies around 0 are considered to be low frequencies, and frequencies around pi and minus pi are considered to be high frequencies. So now when you look at this system response, what is it telling you? It's telling you that frequencies around the low frequency range, in the low frequency range, are going to be attenuated, right? You all understand attenuation? Attenuation means that you're going to reduce. So what is the frequency response? So if I have y, right? We all know that, right? That when you take the time domain convolution, it becomes frequency domain multiplication, correct? So what is this telling you? It's telling you that for an input signal, your h e to the j omega is like a mask you're applying on top of that signal, right? So when you're going to apply this mask on your input frequencies, whatever it may be, and you're taking a product, right? So wherever this is going to be low, the resultant product is going to be low. Low, I said, right? I mean 0, low, whatever it is. And whenever it is high, it is going to essentially follow this thing here, right? Is that clear to everyone? So now, does it make sense why this is a high pass filter, that you can say that from the frequency response, from the magnitude that you see of h of e to the j omega? Is that clear to everyone? Okay. And so this is one of the reasons why we defined the DTFT, right? Because you can do such analysis. Okay. Is that clear? And soon we will also, when we go to the Z transform, you will see that it is actually kind of going to be a super representation of the DTFT, in the sense that the DTFT can be expressed in terms of the Z transform, okay? And so the motivation is pretty much similar even there, okay? And before we go on to the Z transform, let's quickly complete a couple of other properties of the DTFT. Okay, any questions so far? Clear to everyone why we want to define the DTFT? Okay. Right. So let me, to answer that question, say suppose I define an error signal. And what is the energy of my error signal? Yeah. Okay. Any more questions? No questions? Then after we had this basic definition of the DTFT, we derived a number of properties, right? Okay. And then we spoke about what happens when your signal is even symmetric, odd symmetric, right? Then we, and any questions about that? Why is that going to be useful? We will see that in a second, why it's going to be useful. Any questions? Yes. Just as a question, have all of you looked at the concepts of pointwise convergence in the math courses that you have taken? Yeah. Have you looked at? So, can any of you recall the definition of pointwise convergence for me? If you have not, it's okay, because I don't want to get into too much of the math detail, because we want to move ahead with this material. If you recall, go ahead and define it for me. If not, we'll skip over that. Okay, then let's just skip over it. Okay, so there are a couple of other properties of the DTFT that I think we should all know about. One is what happens when we have this type of sequence. So this is our standard backward difference operator, right? So what happens when I take the DTFT of this guy? What do I get? Minus what? Okay, this result is straightforward, right? You just know what to do when you have a delayed version of the signal. We looked at that, right? So that is one result. The other result is a little bit more interesting, and I would like to derive that in class today. So what happens when you have this system? So what is that system? That's the accumulator system, right? We all recall that. Okay. So before we go here, I want us to recall one of the results that we had from last time. So if what did we say was the Fourier transform of this? And what is this we defined last time? That was a delta function in the continuous time domain, right? Yeah. So do you all recall this from the last class? Do you recall your question now? No?
The value of that delta given at 0.
Right. The delta function is not like in the analog, in the digital discrete domain. Like we discussed last time, it's defined only under an integral. So one of the properties that we said last time was that when you do this, so this is going from minus pi to pi, that's going to be 1. Okay. Do you recall the limits from last time? Was it minus pi to pi? I think so. Minus infinity to infinity? Okay, that's the general definition, right? Okay, so let's have this result in our back pocket for now. Okay, so what do we want to find? We actually want to find this. Okay, to find this, do you also recall the transfer function of the accumulator system that we defined? U of n, right? So this is essentially, so I can write this x of n right? Do you all recall that from how we defined the accumulator system in terms of this, right? U of n, right? Okay, now we are going to make use of this result in the following. Okay, so we have this, right? We have x of n is 1 for all n, right? Now can you think of a way of defining my u of n in terms of this signal here? So I want to write my u of n as, say, the sum or difference of two sequences. And we want to make use of this result here. So just draw it out, right? So how is this signal going to look like? This is going to look this way. So this is this x of n that I have here. And what do I want? I want this. Okay? Say I'm fixing this guy to be this. So how would this signal look like? Okay? So you want to say that this is equal to this x of n that we have here minus right? Is that right? Okay. This is one way of doing it. Now what if I gave you another definition? I'm giving you a hint. I'm going to say that this is actually this. Okay? And I want to use this property as well that we have defined over there. So this I'm going to say is equal to minus 1/2 of u of n minus let me make sure I have my notation correct. Or let me write it out. Then probably this becomes plus. If I have a signal like that, do you think that's going to work? Sorry? Let's forget this for now. My u2 of n is this, and my this x of n is this thing here. You want to do that? So you want to maintain this minus sign here. Okay. Okay? Yeah. So now if I add these two things, I get u of n, right? And there is a reason why I defined this signal this way. So now what happens if I take, so right now I don't know how to get the Fourier transform of this, correct? I don't know what it is, right? Yeah, so what is this signal? So this is going to be essentially this, but it's going to be 1/2. So I'm saying 1/2 times this x of n, where my x of n is defined like this. Okay? And my u2 of n is going to be -1/2 when n is greater than or equal to 0, and is going to be +1/2 when n is less than or equal to 0. And I want to subtract this from this. Okay? And why are we trying to do all this? Because we want to find the DTFT of u of n, correct? From these two results that we have here. Okay? So now, what happens if I do this? What signal do I get? Yeah? Do I have a half, or is it just delta? So what do I get when I subtract this thing from here? So what is this going to be? This is just going to be shifted by 1, right? You're going to have minus delta of n, yeah. Right? So how is this going to be? Right? Do you all see that? You just shift this thing by 1 to the right, and you're subtracting. So this thing gets flipped over, and you have minus delta of n. Okay? Right? So now, I can use this result, right? What do I get from here? So I have u2 of e to the j omega times, what is the Fourier transform of delta? So in this case we have a minus sign here. That's going to be -1. Right? So what is u2 of e to the j omega? Right? And do we know the Fourier transform of this u1 of n? By 2, right? This thing by 2. Everybody see that? So now this implies correct? Because of the linearity of the DTFT. Yes? No? So just to be clear again, So this u1 of n we have defined in terms of this constant signal here. We have a 1/2 in front of it. u2 we want to define so that when I combine u2 with u1 in this fashion, I get back my u of n. Okay, and I have tried to find the Fourier transform, the DTFT of u2 of n, using this result here. Okay, and so when I take the Fourier transform on both sides, I just have u2 e to the j omega, and using this result here, I get u2 e to the j omega is minus 1 by 1 minus e to the j omega. Okay, so now I'm just going to plug this result. Let me call this equation 1. Let me call this equation 2, 3, and equation 4. If I plug in 1 and 4 in equation 2, I essentially get the Fourier transform of the unit step function, correct? And what is that result going to be? So I'm going to directly write it out. I have a minus sign there and a minus sign there. That's going to cancel out. And this u1, this is actually 1/2. So this implies let me call this equation number 4. Plus I get okay. I specifically wanted to do this in class because the result is directly mentioned in the book and there is no proof given in the book. Okay, so those of you that are interested, you can make a note of one of the ways to prove it. Yes. This is from the definition. Like we said that when you have a signal like this, okay, it essentially, so this is DC, right? So there is no variation at all in the time domain. Okay, so if you think about it just intuitively, you would feel that the Fourier transform of that should just be have a value at 0, right? There is no frequency content in the signal except a constant DC value, right? But this signal is neither square summable nor absolutely summable, right? So if we try to find the DTFT in the regular definition that we have, it's not going to have a DTFT, right? Because the summation is not going to be finite, right? So in order to overcome that shortcoming of the formal definition of the DTFT, we define this delta function, okay? And this is kind of a way to accommodate such signals in the framework of the DTFT, okay? And so the way we have defined it is that this is going to be this delta function in the continuous domain, okay? It's slightly different from the way we define the delta function in the discrete domain, okay? And also we want the signal to be periodic, right? We know that the DTFT of a signal is periodic with period 2 pi. We did that in the quiz also last time, right? So that is why we have this 2 pi k term here, okay? So it's going to be this delta function that's going to repeat every 2 pi in the frequency domain.
Why that is 2 pi?
Sorry? Yes, so this is to make sure that when you go back to the discrete domain, you have, so when you, what's the analysis, the synthesis equation? It's 1 over 2 pi times minus pi to pi x of e to the j omega, right? So this is to account for that. Okay? So is this clear to everyone? And this is one of the ways, like this is kind of an adjustment we make or tweak the DTFT to accommodate signals that are not square summable or absolutely summable. Okay, and that also applies to U of n, right? U of n cannot be absolutely summed, nor can it be square summable, nor is it square summable, right? So for such signals, if we still want to define the DTFT, this is how we do it. We make use of this initial definition and try to come up with the DTFT of the unit step function. Okay? Yes.
So rather than using U of you can use U of n minus U of n minus 1 equal to delta of n.
Okay.
Now,
So I'm just going to have this 1/2 difference, that's all, right?
then we can get directly.
So that will have a 2 sitting somewhere. When you take the difference, it's going to be 2 delta at some point.
Divided by 2. Fine, no problem.
Yeah.
Then we can get directly the value of U of e to the power j of n. While using U of U2 of n, we have to calculate this. But if we use U of n, we will get directly the value of U of
So you're saying here, what do you want to use?
U of.
No, but that's the point, right? We want to express U of n in terms of a signal that is neither square summable nor absolutely summable. U of n is also a signal like that, and we want to use this definition that we have, and that's why we had to go through all this exercise. If we directly use U of n, then how do you find U of g e to the j omega?
By using this equation only, U of n minus U of n minus 1 by 2 is equals to delta of n.
Okay.
Fine. Therefore, this backward difference can be represented as U of e to the power j omega. 1 minus e to the power.
Right. So basically, according to what you're saying, it's going to be U of e to the j omega is equal to 1 by 1 minus e to the minus j omega. Okay. Right. But this again assumes that you can have this thing is actually square summable, right? Only then you can write out that definition. This is actually absolutely summable. See, the point is that you don't know what this is, right? And you're trying to find it out. Right? Yes. And I completely see what you're saying. So essentially you're saying that correct? And then you want to take like what we did here, right? Yeah. Right? And then you just directly get, so you only get this one term sitting here, right? And so the reason for that, so you're assuming that this thing is existing, and that's why you say that this is how it should be done. But the question is, we don't know about this to begin with because of the way your U of n is defined. Anyways, we'll get back to this later, or we'll have a discussion offline, okay? Because I want to cover some more material today. Anyhow, you have that thought in mind. I did think of what you said, but we'll discuss it perhaps later. So this thing is done. So now, did we define the DTFT of any of these things in the last class, of these signals, delta of n, delta n minus n naught, so on and so forth? Do you recall, do you have it in your notes? Okay. Okay, so the first signal is delta of n. What is this going to be? And we just defined u of n here. So we've done with that. And then this is again an interesting signal. Say suppose I am giving you okay, this is what I am giving you to be your h of e to the j omega. Right? How do I find h of n from here? I go to the synthesis equation, right? Is that the synthesis equation? Yeah. So now when I plug this in, what happens? So this I can ignore, right? Because I just want one period of my Fourier transform, right? We all know that, right? When we are evaluating it, you just evaluate it over one period of the Fourier transform, right? So what does this turn out to be? There might be a 2 pi here. Right? So then the Fourier transform of e to the j omega n is going to be this thing here. Sorry? Where do you not take that term? Okay. But that was when you had continuous domains in both, right? So in case of the DTFT, you remember that the DTFT is periodic with period 2 pi, right? And so that's one of the reasons why we have that additional term there. Okay, so that is that. And then let's come to your quiz question. We've already done that, right? What does that, what's the Fourier transform of that? Right? And we all know how to do that, right? Simply a series summation. Okay? So this is done. This thing here. Now to evaluate this, what result are we going to use? One of the properties of, right. So what is this going to be? This is going to be n times and we know this is going to be what? Do you see that? There's a j. Okay, and you can go ahead and simplify that. we've just done for e to the j omega naught n, right? So how would you do that? So you just write this as plus what? Right? So you can apply this result here. Okay? Okay. So one more question for all of you. So why did we do all this? What did we do first in this class? What was the first thing that we talked about in this class? Do you recall? The first couple of lectures, what did we talk about? We defined signals, right? And so what did we do here? We defined the DTFT of the signals that we initially defined, right? Does it make sense why we are doing this? Okay, and we defined a basic set of signal types, right? We defined the delta function, we defined the unit step function, we defined the complex exponential, right? And so on and so forth, right? So now we know that we also discussed in class that any given signal can be broken down into a series of impulses, right? And then we also saw that an impulse can be represented in terms of step functions and so on and so forth, right? So we can do a lot of these signal manipulations, correct, in the time domain. And so now what we have here is we have defined a basic set of signals and we have defined a set of Fourier transforms corresponding to the signals that we have defined so far in class, right? So we have two powerful tools that we have equipped ourselves with right now, okay? And we've also studied the properties of the DTFT, right? So if you think about it, you already are equipped with a lot of things that you can use for signal analysis already, okay? And one last example that I want to talk about before we move on to Z transform is trying to put some of the things in place. Any questions? So are we sufficiently clear on why we want to define these things? Okay? Because you're typically given a system or you're typically given a signal that's applied to a system, and if you want to find a system response, you can easily do it in the Fourier domain because convolution becomes multiplication. And if you know the basic DTFTs, then you can apply it to any signal that's given to you and try to find a system response, right? Yeah? Clear? Okay. Yes. This sigma? This is h. I'm giving you that this is the Fourier transform of some h, and I want to find what that h is, right? And so I'm saying that it's defined like this. It's a series of continuous domain impulses, okay? And from here we applied the analysis equation, sorry, the synthesis equation. Right, so what does this mean? This essentially means that this signal is going to repeat itself every so many frequencies apart, right? So the sigma is to make sure that your h of e to the j omega satisfies the property that your h e to the j omega is periodic with period 2 pi, and that is why we have this summation here. And if you remember, I erased this thing from here, right? The reason for that is because we want to only look at one period of h e to the j omega, correct? And so from here we come here. But to answer your question, this is to ensure the periodicity of the DTFT. Yes. Sorry, I can't hear you. In which case? Mm-hmm. So you're saying that so essentially you're saying this is going to be convolved. So okay, if you look at it that way, right, you need to, so how are you going to evaluate this? First of all, I'm specifying this thing to you, right? So this sequence itself is going to be, so this is going to be finite in this case, right? So it's your question, are we taking two signals and multiplying them? And then when you take the Fourier transform, we need to be convolving the Fourier of this plus Fourier of this. Is that your question? So this is in the discrete time domain, right? This is a discrete time domain signal. And then we are taking the Fourier transform of this signal here. So if you were to plot this thing, right, how is it going to look like? And it's going to be 0 elsewhere. We can talk offline if it's not clear. Okay? Any more questions at this point? Clear to everyone? Okay?
A to the power and U of n. But if we're taking a to the power and U of n and finding out the DTFT, why there is no DTFT terms come from U of n? Only you are getting the DTFT term of a to the power.
Okay. So that's, so essentially your question is this your question? So I have,
Where is U of n?
is this your question? Where my x1 is a to the n and x2 is u of n? Is that the question? Okay. So like I said, I'm trying to finish something for your midterm, so we'll discuss this offline, okay? You can think about the answer to that. So when you convolve something with this, what do you get? Which one? Right, yeah. So let's quickly get to the Z transform. We'll discuss this offline. I'll try to get you the answer on Wednesday. Okay. So let's move to the next chapter in the book, which is the third chapter. It's the Z transform. Okay. Let's motivate the Z transform. Now we saw towards the end of our discussion of the DTFT that it was not sufficient to encompass all signal types, right? For example, we had to change the definition to look at signals that were not square summable or absolutely summable, right? We introduced the excuse me, the Dirac delta function, for example, right? And we also saw for the case where signals were not absolutely summable, right? So what did we do in that case? When we looked at the low pass filter, for example, we defined the Fourier transform for size m, right? A window of size m, and said that when signals are square summable, then that definition of the DTFT tends to the actual definition as m goes to infinity, right? So that was another concession we made, or try to make the DTFT kind of all inclusive, right? So the problem occurred because of the way we defined the DTFT, right? So do you recall the definition? Right? And everything depended on this summation being finite, right? Or us being able to evaluate this summation, correct? So one of the reasons we want to define the Z transform is kind of, it's like almost a one-to-one analog of trying to define the Laplace transform in the continuous time domain. So do you recall the Laplace transform from the continuous time domain, right? You probably looked at it in control theory, the MTEX probably, right? And the BTEX, in what context did you look at the Laplace transform? Circuit analysis, right? And do you recall when a circuit is stable and unstable and all that? Did you do stability analysis of circuits? So you defined the S-plane, right? Did you define the S-plane? What happens when things are on the left of the S-plane and things are on the right of the S-plane? Do you recall those things? Okay. So the motivation to define the Z transform is very similar to why we defined to the Laplace transform actually. So this is going to be used widely for doing system analysis. If you recall, one of the motivations we gave for the DTFT was that we can try to see how stable a system is or not by looking at the h of e to the j omega, right? We gave an example where you have something in the numerator, something in the denominator. When the denominator goes to 0, your system becomes unstable, right? That we defined for this DTFT, but it's going to be more widely used with the Z transform. And we're going to talk about that, I think, for a long time for the rest of this course, especially when we do system analysis, okay? So one thing also we said when we defined the DTFT, we used this because it was the eigenfunction, right, for LTI systems, right? And so let's look at another signal. So can I write any complex number this way? Yes or no? Yeah. So then the question to you is this also an eigenfunction to an LTI system? Yes or no? So actually the point is that when let me actually define it like that. So now when I have an LTI system, so let me define my h of z to be, or let my x of n be equal to z to the n, okay? This is kind of a direct analog of what we did for the definition of DTFT, right? If you recall, what did we do in case of DTFT? We said that our x of n right? Do you recall that? Okay. So now let's do something similar here. And let's check if this is also going to be an eigenfunction for an LTI system. Okay? So what do you think? You think it's going to be true or not? So how did we define our y of n? So now is equal to what? Right? And so what do I do now? Okay. Again, because of the linearity property and the time invariance property, right? That's how we could actually write it this way in the first place. And now do you all see that? Straightforward, right? I mean, again, all I'm doing is just replacing e to the j omega with z, right? And my z is defined like this. So does this mean, so this is a complex number, right? So I have a complex number multiplying my input signal. So this means that my z is also an eigenfunction for, my z to the n is an eigenfunction for an LTI system. Okay? And the nice thing is that if my r is 1, I get back my DTFT. Correct? Is this clear to everyone, what we have done here? Yeah? So any questions? We'll stop and we'll just discuss at this time.
Similar to DTFT.
Exactly, yes.
I need to be bonded.
Right, right. The reason precisely is because of the constraints that the DTFT has. Now, this is, if you think about it, this is a more general representation of complex numbers, right? And so it is going to give you a lot more flexibility in terms of evaluating this thing here. Let's write it out, okay? So now, if this is our definition, let's write out, let's say that deal with signals in general. Right? This is our definition of the Z transform. Okay? So now, if we plug this thing over there, what do we get? Right? I just plugged in this representation of my Z. Okay? So now what is happening is that this term here is actually going to prove very useful. what I mean by that is, now if you want to look for the stability of the system, right? We want essentially, earlier we had okay. Is that clear? So when did we say that the DTFT would exist? When this summation, we wanted essentially, so the magnitude of this thing is 1, right? So we only cared about the summation of the magnitude of the signal itself. And for the DTFT to exist, one of the conditions we said was the absolute summability, right? In case of the DTFT. Do you all recall this condition? Right? So now the same condition translates to something like this. And we have this additional R term sitting there, and that is what is going to help us a lot when we are dealing with signals that may not necessarily be absolutely summable. Okay? Because especially if R is less than 1, right? You see that in several cases that summation is going to become finite, right? And that's the key, one of the key reasons why we want to have such a definition rather than simply living with that. Okay? The R term is going to give us a lot of leverage in terms of being able to analyze systems or signals that are not necessarily, that don't necessarily have a DTFT. Does this answer your question, Ritvik? Okay. Any more questions? Yes. Here? Yeah. Right. Any more questions? Are we motivated a little bit why we want to look at the Z transform? Okay. We'll do a couple of examples and then things will become more and more clear to you. Yes.
Then why we are using Fourier transform?
Yeah, the reason for that is that you have good fast implementations of the Fourier transform. Okay. And we'll see also how the Fourier transform is related to this Z transform. Okay. We can actually see that right away. Clear to everyone the definition and the motivation? Okay. Now let's see some interesting relations between the DTFT and the Z transform. We've seen one already. So if I have the complex axis, the complex plane essentially, assume that this is a circle for now, but this is the unit circle, okay? And so if you recall the DTFT of a signal, we said that it's going to be defined from minus pi to pi, right? So in the Z domain, that actually translates itself to wrapping your DTFT along this circle here. So you traverse from, so this is this angle is omega. So this is when omega is 0 radians, and then this is when it's pi. And you go from, if you go this way, this also becomes minus pi. Okay. So if you want to interpret what you did for the DTFT, and if you look at the high pass example, right? So we had the magnitude response go something like that. So these 2 points actually map here, and this point actually maps here. So it's almost like if I take this and if I wrap it around on like a circle, that circle is essentially this thing here in the Z domain. So at 0, the response is going to be low, and at pi, the response is going to be high, the magnitude response. We'll try to have an illustration in the next class to show this better, but to give you an intuition, this is what is happening. You're taking this and you're essentially, if I take this and if I wrap it around like a cylinder, right, then this point is going to correspond to this here on the cylinder, and this pi minus pi points are going to correspond to these 2 points here. And that is one relation that you have between the DTFT and the Z transform. Okay. So we have defined it. Let's look at a couple of examples so things are a bit clearer. Okay. Okay, let's go back to the quiz question. So I have now let's try to evaluate the Z transform of this thing. Right? Okay. So now this is equal to yes? Clear to everyone how this is? Okay. So now we now have this condition here, right? So we want, as long as this condition is true, this is the Z transform of a to the n u of n. If you recall what we did in the case of the DTFT, we started upfront by saying for the DTFT to exist, we need this condition, right? In case of the DTFT. But here what are we doing? We are saying that this summation is going to exist if this condition here is going to be satisfied. Okay? So what does that condition mean? It means that my mod Z should be less than or greater than. Right? And so what does that simplify to? So that simplifies to right? So this is my so what happens to my signal when z is 0. 0, right? Okay, let's try to represent this on the z plane now. So this thing exists for all z whose magnitude exceeds and at A there is something known as a pole, and at 0 is something known as a 0. So what happens when z is equal to A? The magnitude of that becomes infinite, right? So such points are known as poles, and in this case at z equal to A we have a pole, and we denote that by x on the z plane. Okay, and whatever I have shaded here is what is known as the region of convergence. So this is the region in the z plane where this summation actually converges to something that is finite. And typically when you have sequences like this, in this case we have a right-sided sequence. The right-sided sequence has a region of convergence that is outside of certain value of z. In this case it is A. Okay, and it is always, you will not have a pole inside the region of convergence for any sequence or system, because if you have a pole inside the region of convergence, it means that there's something wrong, right? It means that if you have a pole, it means that this is going to be infinite, and so the summation is not going to converge to something finite, right? So that's one point you have to always keep in mind, that your region of convergence cannot have a pole present in it. Okay? Any questions? Let me pause here. I think I'll take a few questions and then before we go to the next example. So I hope you made this observation, right? When we start off trying to evaluate a Z transform, we don't try to impose any constraints on your input signal. We instead try to find those values for Z where the transform itself exists. This is a little different from the DTFT, where we want to impose constraints on the signal that you're looking at, right? And so that is one of the key differences that I want you to take away from this example here. Yes, so we have a summation here, right? So we want to find the Z's for which that summation converges, okay? Or is finite. Any more questions? The sum will be finite for Z greater than or equal to. So this, you can go from here to here if this condition is satisfied. Yes. Is finite. Yes. Any questions? Is the motivation clear why we want to work with the Z transform as compared to the DTFT? Okay. Okay, we'll do one quick example before we break. Let's look at something similar. Let me leave this result here. what type of a sequence is that? That's a left-sided sequence. So here we call this a right-sided sequence, right? Because it's only defined for n is greater than or equal to 0, right? So that sequence is a left-sided sequence because it's defined for n less than 0, right? So what happens if we try to find the Z transform of this thing here? I'm going to skip a couple of steps. Do you see that? So I just did some quick change of the, I just flipped this around and I changed the sign here, right? And then I'm going from 0 to infinity and I'm adding 1. Is that right? Yes? Okay. So when will this thing exist? This summation is going to exist when right? So this means a mod Z has to be correct. So what does that turn out to be now? Is that correct? Yeah? Okay. So you see that both of them actually, if you just simply look at this expression here, x of z, they're identical, right? But if I just specify this alone, that is not the complete Z transform specification. I actually also need to specify where the summation is going to converge, right? That's also known as the region of convergence, correct? So that is one other key takeaway from this example. So apart from this is also equally important for me to specify the Z transform of a signal or a system. Okay? So if I were to plot that out here on the same plot, it's going to be this, right? So in this case, I still have a pole, and that pole is still going to occur at A, but my ROC is going to be inside of that circle, whose radius is A. Okay? And so that is one of the things about left-sided sequences. Okay? The ROC is going to be contained within the pole. It still has a 0 and it has a pole. In the first case, we had the ROC lying outside the pole. In the second case, we have the ROC lying inside that pole. And the radius of this region of convergence is A.
It's like for every left-sided sequences, the convergence will be
Yes. Yes. That's a general result that you can have for left-sided sequences and right-sided sequences. Okay, we'll stop here. Are there any questions before we leave? Any questions? Yeah, please don't use the phone in the class.